Good morning. Good morning. I'm Stefan Werkstatter, VP of Sales EMEA at EPC. Welcome to today's webinar, Practical Applications of Gallium Nitride for Motor Drives. Before we get started, I would like to go over a few housekeeping items for today's event. You will have the opportunity to submit text questions to the panel by typing your questions into the Q&A feature at the bottom of the screen. You may send in your questions at any time. We will collect these and address them during the Q&A session at the end of today's presentation. Now I would like to introduce our speaker today, Marco Palma, Director of Motor Drive Systems and Applications.
Thank you, Stefan. Thank you, everybody, for joining this webinar. I will stop my video and start sharing my screen to go through the presentation. And as Stefan said, all the questions you can submit it in the panel, and then we will address the question after the presentation. Enjoy the webinar. Okay, so slideshow. I hope you can still see me. And hear me.
Everything looks fine, Marco. Thank you.
Okay, then sorry, there was a technical problem and there was the Zoom had a problem. I hope you can see now my screen. And today I'm going to talk about gallium nitride devices on application for motor drive application. And I'm going through in this agenda. So I will talk about the application landscape devoted to motor drive, the advantage in motor drive when using gallium nitride devices. What you can do, you can increase the PWM frequency, you can reduce the dead time, and then I will go through some application examples and to show what is the effect of using a gallium nitride inverter to this motor drive application. And some words about motor drive layout rules that are slightly different than the typical rules we've been dealing with the EPC GAMFET for other type of application. And some words about the gallium nitride motor drive reference designs that are available, so that if you want to jumpstart and do your motor drive example, you can do it by using our motor drive reference design, and then a summary, and then we will have question and answer. So if we talk about the landscape and we look on terms of inverter, usually the voltage source inverter is sized with current and also dimension. So if we do a 2x2 matrix on current and dimensions of the inverter, we see that in the bottom left, we have a situation where we need to have the highest miniaturization. And at top right, we have application where there is the need of having a high current. And so here are some example of high current application. And when I say high current, it is above 100 amps, can be 100, 150, can be even 400 amps. Here there's an example where still you need a decent number of current from your inverter, but inverter needs to be small. And we're talking about, let's say, 35 amps or mass, for instance, for an e-bike. And then here we see applications where miniaturization is really important, like a humanoid robot, where you can have a joint that as a not continuous as a steady state, but as an impulse current, they can have up to 30 amps, depending on the robot, depending on the joint, but can have a quite impulsive current. From that point of view, we have developed so far in the last 4 years several EPC motor drive reference design. We have the EPC 9186, where we showcase the EPC 2302, and there are 4 in parallel per each switch. And we have the EPC 9194 and the 9193H3 will be released soon. That is showcasing one or two devices in parallel. And then we have the power stage reference design, where I will go into detail a little bit later, where we have basically 3 integrated circuits, and the 3 integrated circuits are doing the entire inverter. The other 3 integrated circuits you see here are the current sensor. So the inverter is done just by 3 gallium nitride pieces. So looking on the use of gallium nitride in motor drive, one common myth is that, okay, why would you use gallium nitride on a brushless DC motor drive? Usually this application are going very slow. There's no need to have such a fast switching device. And so the common myth is that there's no benefit to using GaN devices in brushless DC motor drive. In reality, what we found is that in reality, there is benefit. And the reason is that you can have a smoother switching, and then I can show what is the increase of PWM frequency and what is the effect of a very small dead time, and then we go through the application experimental result. So if we look in terms of switching, so here we're showing a 5 nanosecond per division example, and we see a switching of voltage in time. And here you see the typical way a MOSFET is switching, and the way the DVDT is going with different segments is also related to the way the reverse capacitance is changing with voltage. And the GaN-FET has a smoother reverse capacitance and a lower reverse capacitance. These are normalized, obviously. There is a difference, a ratio in the capacitance of a GaN-FET given the same RDS-on by a factor from 5 to 10. So here you see how a typical GaN-FET, discrete GaN-FET is switching, very linear switching, and this kind of oscillation really depends on the type of application. In a case of a motor drive, we design all our reference design to be kind of underdamped, so there's really no real oscillation in the switching node. And the fact that the switch is faster and smoother, and there is no reverse recovery because gallium nitride FET do not have reverse recovery, and that there is a lower switching dissipation, this is allowing us operating higher PWM frequencies, and the dead time can be reduced to tenths of nanoseconds. Then, depending on the board, depending on the amount of current you want to switch, it may be 20 nanoseconds, or it may be 50 nanoseconds, it may be 75 nanoseconds. For those boards where some of our customers are doing at 300 amps, they're using 100 nanoseconds. That is really different from the typical values that are used with MOSFET. So then looking at the benefit, we say, okay, the gallium nitride transistors and the gallium nitride integrated circuits, they can switch fast and smoother with zero reverse recovery current. So that means we can increase the frequency, but what is then that we get by increasing the frequency? We can reduce or eliminate the electrolytic capacitor in the DC bus, and also we can reduce the motor losses. On the other side, since the switching is smoother and there's no oscillation and it's always switching in the same way because there's no reverse recovery, we can have a lower dead time. That means higher torque per ampere higher torque per ampere in the same motor. So the motor start operating more ideally, and because usually motors are designed for sinusoidal operation, and then they are used with PWM operation. And the gallium nitride inverter has a better total harmonic distortion. That's why it's improving the total inverter and motor system efficiency. And also by reducing the capacitance, it can reduce the size and the weight, and it makes the inverter can be integrated inside the motor. So let's go into a little bit on detail and let's look on the PWM frequency increase. What does it mean in terms of the effect on the motor? There are several effects, and we'll show you the, let's say, the most simple and clear. The first thing is if you have, in this example, a schematic example, if I have a 10 kilohertz ripple, a 10 kilohertz PWM, I have a 10 kilohertz ripple on the current. And the motor inductance does not change, and it is fixed by the motor design. And the PWM frequency and the input DC voltage are dictating this slope of the ripple current. So this is something that cannot be changed. The only thing that a designer can do is increasing the PWM frequency. So you see the slope is the same, but since it is going under kilohertz, you have a lower ripple. Then if you look the effect of this ripple in terms of losses in the windings, then you can see that going from, let's say, 10 kilohertz in this example to 100 kilohertz at 50 volt DC, here we get 3 times reduction of the ohmic losses in copper windings. Then, depending on the motor, but the other things that happen is that this ripple across the current is generating small hysteresis loop in the magnetic circuit of the motor, and these hysteresis loop are also responsible of energy waste. Going higher frequency makes this hysteresis loop smaller, so there's less losses in magnetic components in the magnetic circuit, of the motor. Another important effect of the frequency, PWM frequency, is that if you see the inductance, typical inductance in the motor, if the current increase, the inductance is doing, the motor may enter in a weak saturation, and then the inductance can start becoming smaller. And this effect is visible when the current becomes bigger. And here in this example, we have a 20 kilohertz MOSFET driving MOSFET inverter driving a motor with 500 nanosecond that time. And the sinusoidal current, which is here, is 46 amps peak. And I'm zooming the current here at the zero crossing, and I'm zooming the same current at the peak. And here what we see is that since this motor is very low inductance, already during the zero crossing, there is a 3 amps ripple, and you can easily see that the current is rising at 3 amps on 3 microseconds on the zero crossing. But when it comes to this point, we're to the 46 amps peak. Here you see clearly that the motor is entering this area because there's a ripple which is higher, and if you do the di dt, you see that this is higher ripple, and you have a 15 amps ripple on top of the peak of the current. This is responsible of the motor heating and also vibration and loss of energy. If you, in the same motor, use 100 kilohertz gallium nitride inverter, what you get 100 kilohertz, 50 nanosecond at times, you have still ripple, and the ripple, if you see, it is changing the slope, because here you have 1 amps in 1 microsecond, here you have half amps in 1 microsecond, but you have a more stable operation, less ripple on the peak. So the gallium nitride inverter is able to utilize the motor also in this area without excessively increasing the temperature of the motor itself. And another effect important is, especially in battery operated system, like could be, for instance, an e-bike. You have a battery, you have cables going to the inverter is integrated in the motor, but then the cables are responsible for EMI because there is a current ripple and voltage ripple. And then usually customers need to dump a little bit this ripple by adding some inductance at the beginning, and then since usually these applications are running at low frequency, 16 kilohertz, 20 kilohertz, and usually there are electrolytic capacitors. When talking about capacitors, it's really important understanding that if you use electrolytic capacitors, the electrolytic capacitors are sized in terms of the RMS current, which are that's due to the technology. So, and a rule of thumb is that given the maximum phase current RMS, the RMS on the total RMS on capacitance is something like 65% of it. So it really depends on what is the amount of this current, which is really dictating how many capacitors you have to put in parallel. Is not really it is not really the ripple that is dictating the capacitance, but it's the RMS current. So if you instead work with different type of technology like ceramic capacitors, then is a different story, because in that case, while the electrolytic capacitor are sized with RMS current, the ceramic capacitor really sides with the voltage ripple. So if you use ceramic capacitors, you are sizing the DC bus inverter based on the voltage ripple that you want to accommodate on your application and also on your cable. And depending on the material of the electrolytic capacitance, and depending also on the capacitance of the capacitor, you have usually the optimum in this area, in the area of the hundreds of kilohertz. So that is also giving another important effect. So going into the dead time reduction, so why we insist on reducing the dead time? First, because you can do it, and you are doing a voltage source inverter, and a voltage source inverter is supposed to impose the voltage to the motor. However, when you are doing the zero crossing of the current, where basically the inverter is not really, it's kind of not really dictated by during the dead time, the behavior of the inverter is not dictated by the switches, but it's dictated by the load. So you have this discontinuity, because with positive current, you have a certain behavior, and with negative current, you have another behavior. These discontinuities here are reflected into the current, but also you have 6 discontinuities because this is a 3-phase load. And we'll see later what this discontinuity mean, but with the same frequency in this example, gallium nitride inverter, but very small the time. So here we're comparing 500 nanosecond versus 21 nanosecond. We get very nice voltage shape applied to the motor, which in result becomes a very nice low distortion sinusoid. That means that if we compare again on the left, 20 kilohertz 500 nanosecond that time, we get in the torque, this is the FFT of the analog signal of a torque transducer put in the motor. We get an harmonic in the torque because of the dead time. And this torque in the harmonic, you don't want to have harmonics in the spectrum of the torque, because harmonics means, vibration. You just want all the spectrum to be concentrated here in the torque. And once you reduce the dead time, the same analog signal, you see here, this harmonic completely disappear. And that means the same signal, the same current is just having more spectral components and a low frequency. That means really is making the motor move. Looking at the differences clearly from the input voltage, input current, and output current. On the left, you have 20 kilohertz, 500 nanosecond. Input current has a very big ripple, and the input voltage is basically a square wave reflecting the duty cycles imposed by the inverter. And the phase current has its own ripple across the voltage. Here, basically, we're zooming here at the peak of the current. While doing 100 kilohertz, 21 nanosecond that time, everything gets better. The input current is smoother. also looks like more sinusoidal. The input voltage is a triangular voltage, which is less component, let's say less harmonics in the spectrum, and the phase current has a lower peak to peak. And the difference here is that in the same operation, this inverter has an inductor and two electrolytic capacitor, while in the same operation condition, the inverter on the right, based on gallium nitride, is using capacitors, just ceramic capacitor. So going into application examples, we see in the application examples, starting with e-bike in a light load. And okay, the mission profile of e-bike is not just light load, is mainly high load when you going uphill or you're just starting from the traffic light. But most of the time it's light load because you are going in a flat region, you pedaling, and then you already have inertia, and the motor is assisting you, but it's not assisting you with the highest torque. And what happened here from the MOSFET inverter versus the GaN-FET inverter is clearly shown here. The input inductance and input capacitors, that was shown also in the previous slides. Input inductors, there's no inductor in GaN inverter, and there's just ceramic capacitors at the input. And you can see clearly that it's almost the same speed, but the torque is slightly higher on the right. And this is generating higher mechanical torque generated by the motor in the same condition. That means it's not really the inverter getting higher efficiency. So the inverter here has the same RDS zone as the inverter on the right. So both share the same RDS zone resistance. And whatever you get from an advantage from the inverter gallium nitride, because lower switching dissipation, is then reduced because we increasing by a factor of 5 the switching event. Okay, that's why the inverter efficiency is almost the same. However, what is changing is the motor, and we are having now more current in different applications that are more customer in different applications that are testing this, and they're really recognizing that based on their existing inverter with MOSFET versus gallium nitride inverter, putting their motor in a dynamometer bench, and they seeing an increase in the efficiency of the motor itself. Another example is if we take a drone with trapezoidal commutation. In this case, we have a motor. This is a motor for a drone. Actually, I'm showing the scheme of a test bench we've been using in the lab. This motor, I'm talking about propellers that have 1.7 meter diameter. So we're talking about a motor that can lift during the takeoff can lift 30 kilos. So we're talking about quite important motors. So we connected this motor to a platform fixed to the ground and to a stand. And the inverter is usually either inside the motor or just in the arm of the motor. And here is an example. What we did, we first used the original inverter. And then after a while, we used just to remove the original inverter and plug one of our reference design board to drive the motor, okay? And the criterion to check the difference between the MOSFET inverter and the GaN-FET inverter was simply looking at the input power. The voltage, input voltage is the same, is given by battery, and then looking at the input current and measuring the input power going to the motor in the exactly same aerodynamic condition. And because the load of this motor is given by the propeller, and since the system is the same, is not changed if the propeller is running 2000 RPM, then we assume that the load is the same. And here you see, in this case, is a drone, original drone with trapezoidal block commutation control. And you see it as given speed. You see that this is quite common. I know this is a cheap solution, but it's really inefficient. And you can easily see it because there's always 60 degrees of during when the 60 degrees here, 60 degrees there, when one phase is escaped off because it is a sensorless trapezoidal control. If you compare the gallium nitride inverter with sinusoidal sensorless field-oriented control running 80 kilohertz, then you see that in the same condition as a very nice sinusoidal waveform. And then by comparing the input power and then doing the difference, so how much the original inverter is consuming more given the motor speed, we see that at this 2300 RPM, the motor, the original inverter is consuming more than 450 watt than the gallium nitride inverter with the same motor and same propeller. And if you consider that a typical agricultural drone has at least 6 motors like this, then you can do the math, you can multiply, then you can see that during operation, just by changing to gallium nitride inverter, it can be saved several kilowatt instantaneous power. Okay, but then we tested also against sinusoidal commutation, because then sinusoidal commutation drones are there, but usually they run very low frequency, like 15 kilohertz, 16 kilohertz. Exactly the same stand, just a different motor and propeller. But again, we're talking about motors that are able to lift 30 kilo during the startup. And here you see the original waveform of the original MOS inverter. Is still sinusoidal sensorless field-oriented control. However, there's a lot of ripple on the current because those motors very low inductance, and the frequency, PWM frequency, is low because of the MOSFET inverter. While here you see how a GaN-FET inverter, in this case, was running 120 kilohertz for this motor, and it was showing very nice waveform. And again, we made the difference. So what is the additional losses of the MOS inverter compared to the gallium nitride during the operation? And here you can see that at 3000 RPM, the difference is smaller. We're not talking anymore about 450 watt, but we're still talking about roughly more than 25 watt. Again, if you do the math and you multiply this by the number of motors in the drones, then you understand that the motors themselves become more efficient, and then the system become more efficient. So I just gave 2 examples from application point of view. The next slide, I just want to go through some basic hints on how to do a layout when using GaN-FET for doing the GaN-FET inverter. And so some guidelines. This will become a more, let's say, more comprehensive guidelines in the future. Maybe we can dedicate then in the future another webinar to this. So the most important thing, which is common to all inverters and all converters who are using gallium nitride transistor, is minimize the common source inductance. The common source inductance is the shared inductance between the gate loop, the shared path between the gate loop and the power loop. So since the GaN-FET transistor have very low threshold and compared to power MOSFET, so the typical threshold of GaN-FET transistor is 1.5 volt. And considering that there is a typical voltage for the gate, which is 5 volt for the GaN-FET, then it's better minimize the common source inductance to reduce the dissipated power. For motor drive, then it becomes really important using thick copper in the first layers where the GaN-FET are attached to. And the reason is we need to reduce the resistance in general of the inverter, and the resistance is not just RDS on. What I seen talking to customer, most of the customer always talking about the RDS on of the transistor, of the MOSFET, but they don't talk about the resistance of the interconnection of the PCB, of the IMS. This is really important, and it needs to be minimized because it's otherwise dissipating energy and is increasing temperature. So we strongly recommend using 2 ounces, which is 70 micro of copper on the layer where the devices are attached. And then the first inner layers having already 4 ounces, so which is 140 micro, so that these layers can really bring the current and also take the heat away. Another important thing is using vias in pod to increase the heat transfer. Here you see on this thermal simulation, these are finite element analysis simulation on a half bridge of an inverter, or actually this of a converter. Here you see on the left, there are the EPC devices just attached to the PCB without any via. And you see that the heat is basically staying all on the devices. Then in the center, we have an example of a layout where the vias are just nearby the devices, but not really under the devices in the pad. And on the right, there is the same example where the vias are exactly under the pads of the device. So it is clear that in the right, you see that color is more uniform because the generated heat spreads immediately across the PCB. It can go through the direction so that it can be removed easily by an heat sink. Another important thing is that the DC bus capacitor have to be distributed in a way that each switching cell, and here an example, this is a switching cell for the phase U, this is the switching cell for the phase V, and this is the switching cell for the phase W. You need to make sure that the DC bus impedance, DC bus plus, and the impedance to the DC bus minus is the same for each switching cell. This is clearly a symmetric design. You see all the capacitors, ceramic capacitor are put clearly symmetrically versus the switching cell, and the output to the motor is here. And when switching less than 5 volts per nanosecond, which is the case in our motor drive, the difference between motor drives and the other, let's say, DC-DC converter is that in the motor drive, we don't switch fast. We switch to the, let's say, the minimum, which is helping from EMI point of view and helping from a winding insulation point of view, but not more than that. But if you are not switching fast in terms of the VDT, it also means that the IDT is not too big. That means there's no need to do what it is called the internal vertical layout, which is very important for the DC-DC operation or for very fast VDT operation. So if you look here, there is no high frequency capacitors in any of the switching cells. The dual capacitors here you see here in this board are in the top layer here are because this is a power stage. There is a gate driver integrated with the high side and low side GaN-FET, and these are the bypass capacitor for the power supply, which is good rule to put them next to the integrated circuit. But there's no high frequency decoupling of the switching loop, power loop, and this is really helping in a motor drive because the switching waveforms are very smooth, but then we can reserve all the copper we need we can reserve all the copper we need for the DC bus. And the DC, so this is DC bus plus, this is DC bus minus, and the copper here is for the phase. So it's really important using the layers for current and heat transfer. So another important thing, which is different from the CDC, is that the first inner layer does not need to be a ground return. Use all layers for the current and for the heat. The other important thing is you need to minimize the DC resistance of the copper. And how can you assess the DC resistance? Better using a tool that can be used to predict the DC resistance. For instance, we use Altium software, and within Altium software, there is a AkiSite power tool analyzer, which is a part that you have to purchase. It's a kind of a third-party software that you can plug in. It's a plugin you have to purchase for Altium. And then it helps you in analyzing your PCB and telling you where are the bottlenecks, where the DC resistance is bigger so that you can minimize it. And it's also important minimizing the device interconnection resistance to the PCB. And with the same tool, we analyze the current density. And the simple trick is whenever you see current density going high, that is related to a resistance part that will be high and will be detrimental to your inverter. So going into these things and with simple rules, we developed a set of EPC reference motor drive boards starting from 6 to 20 amps RMS. These are based on a power stage. As I told you before, a power stage is a PQFN device which has the gate driver and the high side and the low side, the power GaN-FET integrated into it with the exposed die on top so that it helps in having very good, efficient topside cooling. And we have different types of, we have actually 3 sides of these. I mean, the size is always the same of the package, but the sides in terms of resistance, RDS-on of the power GaN-FET is different. So it can go from 6 to 20 amps RMS. Then we will be releasing soon in these days the EPC 9193. There is 9193 as one device per switch, EPC 2619, and the 9193HC as 2 devices per switch. And this is a chip scale package, and it's very small device. This reference design is showing how to use phase shunt resistors or leg shunt resistors. While I forget to say, this example of reference design is showing how to use all sensor IC for current sensing in the phase. Going high on current, we just released it in January, and between December and January, the EPC 9194, which is showcasing the EPC 2302, which is 100 volt, 1.4 million typical RDS-on. And this is also PQFN with the exposed top, so very good for topside cooling. And one of the, let's say, more used reference design board is this EPC 9186, which is able to do 150 amps RMS, steady state, obviously with a heat sink and with some airflow on the heat sink, because it is a demonstration purpose, it's not a final product, obviously. And this is able to reach also 200 amps RMS peak operation. And we are also working on a new board. As I told you, 9193 and 9193HC will be released in the following weeks. They are already done, ready and tested. We're working at this moment on raising the voltage. So we're working on new demo boards which showcase the EPC 2305, which is a PQFN device, 2.2 million, 150 volt, 2.2 million max. And this is 96 volt, one single device per switch, and 4 devices in parallel per switch. And then we also working on a 150 volt operation with EPC2304. EPC2304 is our PQFN 200 volt device, which is currently 5 million, if I'm not wrong. And we will be releasing the single switch version, single device per switch, and also 4 device per switch. And in the future, we'll be releasing also, let's say, a revised version of our IPC 9194 and EPC 9186 with the 100 volt Gen 6 2361. For your information, the EPC 2361 is 100 volt device, less than 1 million typical RDS-on. I think it's the smallest device in the world that can exhibit such capability. And if you look on all these reference design, they come with the same connector here, because here there's a power inverter, there's a current sensing, temperature sensing, voltage sensing, DC bus, ceramic capacitor, and overcurrent protection. Okay, all the boards share similar architecture. And then how do you test the board? So the board looks like this, a 3-phase inverter going to a motor and a connector. Then we have a provision of several adapter boards for, let's say, the most common microcontroller for motor control, like, for instance, the ESP33 from Microchip, or the Nucleo for different types of ST controllers, STM32 controllers. And we also have the Texas Instruments adapter, which is this green board. And that works not only with the Piccolo, it works also with the 379. I know that there are customers using the same board with the 379. And we just released in January the adapter board for the newest platform from Renesas, RA60Q. This one in the picture is the RA60Q that can drive 2 motors, and the RA41, which can drive only 1 motor. And also our board comes with a generic interface just to do a breakout board to wire the signal to your existing controller. So going to summary and then opening for question and answer is that EPC devices, gallium nitride, FET and gallium nitride integrated circuits allow smaller, lighter, and quieter, and more accurate motor drives. And given the same RDS-on, the devices are smaller, they have lower switching dissipation, and they have no reverse recovery. So by using gallium inverter, you can make your own motor more efficient. And that's it from my presentation, and I can open now to question and hopefully hope you enjoy my presentation.
Thank you, Marco. Now we are going to begin answering the questions submitted during today's presentation. As a reminder, you still can submit questions by typing your questions into the Q&A feature at the bottom of the screen. Marco, our first question is, motors need below 500 volts per microsecond. Scan is much faster. Required dampening loss energy of LC, delta V over delta T filters make them useful to less than 2 kilohertz PWM. What would be your solution for a GaN inverter with greater than 60 kilohertz PWM for reliable motor isolation?
So the thing that I said during the presentation is that we have a different approach between, let's say, typical converters and motor drive inverters. The typical converters, AC/DC, DC/DC converters, we're using GaN-FET. We usually tend to go as fast as possible to minimize the switching dissipation from the devices. In that case, there's no, let's say, there's not the problem of winding isolation. Instead, for motor drives, usually there are 2 types of problems. I would say 3. One is the winding insulation. The other one is bearing, which can have a spark problem. And then there is EMI problem. So I would say that in my experience, it's quite common and typical to use 5 volt per nanosecond switching in the motors, okay? So the question here is asking for 0.5 volt per nanosecond, which is, I will say, really, really extremely low. So reason to go so low, it's usually due to EMI constraint in some specific application. From the winding isolation, usually a safe value is 5 volt per nanosecond. 5 volt per nanosecond is what our reference design do. That's what we usually recommend. And what I saw our customer doing two different things. Either they go, let's say, 5 volt per nanoseconds and they go directly to the motor without doing any filtering at all. And usually they also do integrated motor design. So that is also reducing the problem of EMI. And there's no problem for the winding insulation in this case. All the other possibility, some customer doing this, I would say a reduced number of customers are doing this, but they do it. They go very fast at high frequency, something like above 200 kilohertz. And they use a filter, which is quasi-sinusoidal filter at the output of the inverter, so that the cable and the motor is not seeing the DVDT. It's just seeing a kind of either pure sinusoidal waveform or a quasi-sinusoidal waveform that is then not giving problem either to the winding nor to the MI. So summing up, 5 volt per nanosecond is the typical value. Who wants to go below 5 volt, going down to 0.5? Sometimes it's really it depends on the application. Sometimes it's not because of the motor insulation, it's because mainly of the cable, and the cable, unshielded cable, can generate EMI. But it's a trade-off. You could have, let's say, a better wiring and then have less dissipation. That means also less heat in the inverter. It's not necessary to go 0.5. It's quite good practice going around 5, even 10 volt per nanosecond.
Thank you, Marco. Another question is, when it comes to industrial motor drive applications, where the drive is inside a cabinet and connected to the motor through a probably long cable, there are additional things to think about. An increase of switching frequency will cause additional cable losses, and the high switching slope will cause significant overvoltages at the motor terminal, causing additional losses too. Do you have any experience up to which cable length the GaN application, 100 kilohertz versus 10 kilohertz, is more efficient than silicon? Drive with about 60 volts DC and several hundreds of watts.
Yeah, so in terms of cables, what I'm seeing is that, first of all, when cables are really long, one thing that is starting to happen is that some customers are considering going multi-level with the GaN FET. So having lower voltage devices doing several levels instead of doing just 2 levels, so that the overall DVDT is reducing. The other type of approach is really putting a filter before the cables and then going into the cable in a sinusoidal or quasi-sinusoidal way. The difference is this: if you do an inverter based on MOSFET, you do not have this possibility, because the problem is that MOSFET cannot switch very, very fast. So if you want to do, either you go very, very slow, or if you want to switch a little bit faster, then you need to put a filter, but this filter needs to be very big. With a GaN FET, I'm talking about more than 1 meter cable. I'm talking about several meter cables. I'm seeing two types of approaches. One approach is, as I said, there are customers which are really raising the frequency and raising also the DVDT, because then they are filtering just after the inverter. And since they're going fast and high frequency, the filter is smaller. And then the cables are not experiencing any reflection because of high DVDT, and also the EMI is reduced because the voltage going into the cable is, as I said, either quasi-sinusoidal or pure sinusoidal. This is something that can be done with the GaN FET. The other type of approach I'm seeing, at least being studied, not yet in a product, but being studied, is that going multi-level, because the multi-level again is simply dividing in several levels the voltage, making it by nature already quasi-sinusoidal, and also reducing the DVDT input to the cables. In that case, the idea is going multi-level without using any filter. On a practical, following this question, on a practical level, I'm seeing customer trying to use less than 1 meter cable or 2 meter cable, the gallium nitride inverters, but there's always a trade-off between EMI. It's not really a matter of reflection in this case, it's really a matter of the EMI generated by the cables. And so some customers really slow down the devices, and some other customer invest a little bit more on the cables and don't slow down the devices. And when I say investing more on the cable, I'm saying they shielding the cable.
Okay, thank you, Marco. There was another question on page 22, the circuit. Maybe you can move to this slide.
Mm-hmm. I will go to page 22. Oh, 22. Okay.
Okay. There is plenty of empty space on the PCB. Why is it designed in that way? I would expect a size to be minimized.
Okay, the idea here was, let's put this power stage into the PCB, and we were using an existing heatsink we had before, and we want to see how much current we can get from these small devices. It really depends. It's a thermal problem, okay? It's really a thermal problem in general. When you start working with gallium nitride in motor drive, first you think about the thermal design, the thermal circuit you have available, and the thermal budget you have, and then you understand how much you can dissipate, and then you understand what you can do. Here we wanted just to add the highest current we could. Just consider, just to give you an idea, that this device is 5 millimeter. So here we're talking about, we'll say 2.5 centimeter on X direction and maybe 4 centimeters on the Y direction. So I agree, if the space can be reduced a lot. We will be designing a similar circuit in the future with, a smaller dimension. Obviously, what is the trade-off? If I reduce the dimension of the copper, then I'm gonna have lower current capability of the inverter. It really depends on how much current I want to drive. So we still testing this board here. We're talking about 20 amps RMS steady state, but we still didn't finish the test, and we will see if we are able to go even above 20 or even 25 amps RMS steady state, and then we need to see how much we can do in peak operation. Peak operation depends on your thermal capacitance, okay? So if you have a good thermal capacitance, you can have a bigger peak operation. If you have a small thermal capacitance, then you cannot have a big peak operation. And the copper around the device helps you in terms of thermal capacitance. So it's just a trade-off, depending really on the application, what you want to do and how much current you want to process.
Okay, thank you, Marco. Then there are two questions from one attendee. One is, with your measurements, it seems like you're using an open loop control. Question is why?
No, some measurement that I showed during the presentation, some measurement are, so the measurement, for instance, in the e-bike is, okay, there is only one which is open loop I can show. All the other are closed loop. So this one, which I was showing here, it's field-oriented control sensorless. So this is a field-oriented control sensorless. And so closed loop at a given speed. This is the e-bike. Then the drones is also field-oriented control sensorless closed loop. The original is trapezoidal. Our is field-oriented control sensorless. And also this case of the drone is field-oriented control. The only case where we use the open loop to test was when I was showing the saturation effect. This one is an open loop control, but from the concept point of view, it doesn't really matter. I mean, what we're showing here is how to put, to how the motor behaves and inverter behaves when the motor is driven such high current. Okay.
Thanks, Marco. And the other question is, have you tested those designs up to normal conditions, such as rotor lock tests?
Not personally, but our customer are doing. Okay. So again, it is a point of how you do the control. If your control is a trapezoidal control, which is doing a cycle by cycle current limitation, then and you go into locked rotor, then you may have usually it's a thermal problem. It's not really a problem in terms of the device itself. If you're doing field-oriented control, sinusoidal sensorless, then even the locked rotor is something that you can sensorless or with sensor. So it doesn't have to be sensorless. With sensor, then even the rotor locked is something that you control because you control the current all time. So what I've seen, our customer that have been working with the trapezoidal old sensor schemes and had a problem of a locked rotor, and they had to design their inverter to be able to do 100 amps RMS. Then when they went into gallium nitride, then they moved from gallium nitride inverter doing not trapezoidal, but doing sinusoidal field-oriented control. Then they came out to reduce the specification for the inverter because they realized they don't need to be anymore able to deal with 100 amps in the rotor rocket, but 65 amps in their case was okay. So the main point is really thermal. Look what is your worst condition from thermal point of view and check if your system from thermal point of view is able to do it. So from that point of view, rotor lock or operating condition, a low frequency is not really making the difference.
Okay, thank you, Marco. Then one more question. The DC link capacitor that I mentioned is not related to switching frequency, but is only based on the factor 0.65 times RMS current of the phase currents. So increasing the switching frequency will not reduce the number of DC link for the same phase current?
Yes. So the main point is this, okay? Really, each of the electrolytic capacitors can deal with a certain amount of phase current. Okay, so if your system is doing, in this case was I need to remember, it was 35 373. It was something like they needed two in parallel because one couldn't hold the RMS current. So the number here is 660 microfarad because each of them couldn't do more than 5 amps RMS ripple current, or 3 amps RMS ripple current. So really the value you're putting here is not decreasing with frequency because your ripple stays the same. And the RMS current stays the same. So if you're doing a 35 amps RMS phase current inverter, it will be 35 at whatever frequency you want to use. That's the difference between the electrolytic capacitors and the other type of capacitor, which instead you are designing for the voltage ripple and not for the capacitor current. So that's the main difference. So the answer is yes. If you stay with the electrolytic capacitance, it's the RMS current in the electrolytic capacitance, which is really giving you the problem and doesn't change with frequency.
Okay, and then the last question for today. If we use vias for heat transfer, will it not add more inductance to the power path?
No, if you consider that what we do is that we really make, I will try to show it. I don't have a slide for this that show it clearly, but let me go into one that was here. Okay, I can go here and try to show here. If you consider this area here, and this area is DC bus plus, and then on the first inner layer there's another copper which is again DC bus plus. So if I put VS here, they will interconnect this part with the DC bus plus on the first inner layer and the second inner layer. So it's just making the copper more solid. It's not interrupting other layers. The big difference between the motor drive inverter and the DC-DC converter is that we are not using a return layer in the first inner layer because simply we don't have capacitor on the top. So it is not increasing the inductance. For motor drives. For the DC-DC converter, partially yes, the answer to your question is yes, because the first inner layer is a ground return. And if you put vias, then you're interrupting a little bit this ground return. So you have to put these vias in a way that in high frequency, the ground return is not interrupted too much. Okay. And I think we are around the hour.
Yes, so kind of perfect timing. So thank you, Marco, and also thank everyone for attending today's webinar. So if you have any additional questions, please send them to info@epc-co.com. I repeat, info@epc-co.com. You will receive a follow-up email within 48 hours with the link to the recording of this webinar. And thanks for joining us today, and enjoy the rest of your day. Thank you.
Thank you. Bye-bye.